Okay, we continue the Phasor circuit analysis, right? We use the Phasor form, which represent the sinusoidal signal, right? Volt and amp. V and I. When we apply this type of signal to the device, we have three types of device, which is the resistance, capacitance, and inductance, right? So what happens if we apply sinusoidal circuit to resistance? So we have the waveform in sinusoidal form, right? And when we supply the voltage into the resistive circuit, the current will be in the same angle with the voltage, and the power is the voltage and current together, right? So in this case, we can calculate the uh, current and the voltage in the relation the same as Ohm laws, right? V equal to I and resistance in RMS in phasor form, right? In phasor form. It means that we have V in phasor form, I also in magnitude and angle, right? In phasor form. Yeah. So we can just use simple calculation when we supply voltage to the resistor, right? For example, if I supply 220 volt RMS, 220 volt to 10 ohm circuit, what is the current? The current would be V divided by R equal to 220 divided by 10. It's become 20 ampere. So the current will be 20 ampere in RMS term, okay? In RMS term. So this is very easy to calculate the sinusoid waveform when we transform it to phasor value, okay? Phasor value. And what the angle of the voltage, for example, if the voltage is 220 and 50 degree, we supply to 10 ohm. Similarly, our current will be 222, right? 22 with 30 degree also. Okay, it's the same angle, right? Because the current and voltage will be the same angle, right? When we supply it to this type of load, for example, the resistance load, for example, the incandescent lamp, okay, incandescent lamp, not fluorescent lamp, not fluorescent lamp, okay, not LED lamp. The incandescent lamp is a very old type of lamp. Okay, have you ever seen this kind of lamp? Yes. Okay, you can know about this type of lamp, right? Okay, still you use it in your home, right? Someplace? No, no use. I think in your home you don't use it anymore, right? Okay, but you can see it somewhere. Okay, we use it for some special purpose now, like for decorate, right? For decorate in the restaurant or in the jewelry or in the exhibition, right? This type of lamp will give a good color than fluorescent lamp. Okay, ion, right? Ion is also the resistance inside. Okay, it's the resistance inside and it's produce heat for us, right? And the heater also, right? Heater also the resistance inside and it's produce heat for us, right? This is the type of resistance load. Okay, and we have another load. This is resistance in phasor form, right? Which I explained, right? If the voltage have theta angle, the current will be in the same angle, right? So this is the voltage and this is the current. It will be in the same angle, right? In the same angle. No phase shift between voltage and current. If we draw phasor of voltage, we will have the phasor of current in the same direction, okay? In the same direction. So we can use this formula to calculate resistive load for AC circuit. But V and I is in phasor form. Okay. Then we also have inductance type of load, like transformer, motor, and some induction type of lamp. Okay, inductive lamp. For example, fluorescent lamp will act as a kind of inductance. It will have the inductance inside. Okay, and if we have the inductance, the phase of current will shift by 90 degrees because the current is from what is LDI by V is LDI by dt, right? If I in cosine form, for example, if I is cosine, I cos omega t, right? If I is cosine, what is the derivative value of cosine? The cos is minus sine, yes. And if I is sine, derivative of sine is cos, right? So it's shift phase by 90 degrees, right? In this case, right? So when we write down the phasor form, the inductive load will provide 90 degree phase shift to the in between voltage and current, and it will make the current lag voltage by 90 degree. Okay. Right? In this case, this is voltage waveform. But if we supply voltage to inductive load, the current will shift phase, right? By 90 degree, right? So in this case, we represent when we did sine omega t plus theta d by dt. What happened? You get d sine, we get cos omega t plus theta, and omega will be there, right? Then here is the form of phasor. In this we divide in phasor form. So the inductance L will be multiplied with the angular velocity, right? And it shifts by 90 degrees here. So the formula becomes the voltage in phasor form equal to J omega Li. Okay, J means shift phase by 90 degrees, right? Here. The current will shift. So if we have the voltage with this vector, the current will be here. It will have an angle between voltage and current by 90 degree. Okay, 90 degree. So current multiplied with phase shift by J value or 90 degrees become the angle of the rotate, right? So you can see that theta V is theta I plus 90, right? Theta V is theta I plus 90. Okay. And on the other hand, for capacitance, okay, capacitive load is inverse of inductance and of inductance. So the formula is I is C dV by dt, right? If this is in sinusoidal form, it will shift by 90 degree also. But in this case, the voltage will lag the current by 90 degree. Okay, and in this case, V would be 1 by omega j, right? Here, if we solve from this, it's 1 by omega j, absolute I, theta I, right? So in this case, the uh, the current will lead voltage by 90 degree, right? If we do not write down J here, we can say minus 90 here, right? Okay. Minus J mean minus 90 degree, right? Okay, minus J is here. Minus J is here, right? Yes, minus J mean 90 degree, right? Okay. J mean I'm sorry. J mean I in complex number. Okay. So when I talk with EE student, I don't need to make this condition. But J is I. Okay. Uh, if we have like 3 like this. Okay. What is this vector? What is this vector? Four plus J3. Okay. This is imaginary part, right? This is real axis, imaginary axis. We use J in electrical engineering because if we use I, we will confuse whether it's the current or not. Okay, so when we write the complex number, most electrical engineer will use J. Okay, so I use J here. So okay, this means I. What is I? I is 1 minus 90 degree, 1 and 90 degree, right? It's 90 degree. Okay. Or I is square root minus 1, right? In this case, this is I. If I multiply 4 multiply with J, it means that it becomes J4. It means from 4 and then multiply 1. It is similar to 4 with 0 degree. Multiply with 1, 90 degree, and it's become 4 and 90 degree, right? Okay, so 4J is 4 and 90 degree. Okay, you get that? Okay, for J4 is 4 with 90 degree angle, right? Okay. When you multiply complex number together, when you multiply two complex numbers, what do you do? What do you do? The magnitude will multiply together, right? And the angle will add together, right? You do like this. If you multiply 10, 30, multiply with 5, 20 degree, what is the result? 50, and then 50 degree like this, right? Okay, so it's okay. Okay, and this is the calculation for capacitance. The capacitor in your life, in your daily life may be rare, right? But in the laboratory it's there, and in the factory it's there. They use the capacitor in their factory to solve for the phase shift of current and voltage to decrease the phase shift between current and the voltage because the load in the factory have a lot of inductance load. If we have so many inductance load, it will make the current lag voltage too much, right? And it will come out with one factor we call power factor. So I don't think I will talk about this, okay? But anyway, if the current lag voltage a lot, if you have a problem, right, in your power usage, right? So they use the capacitor to solve this problem, okay? So in the practice, uh, both load we have load with uh, maybe the load is mixed with R and L and C together. Okay, R and L and C together. So we can write down the load in the form of impedance. We call impedance with a mix of resistance, inductance, and capacitance. Okay, and inductance and capacitance will be in the imaginary part of the calculation, and the resistance is in the real part of calculation. Okay, so we call this factor as impedance, and the inverse of impedance we call admittance. Okay, like we have earlier we have resistance, right? Resistance, right? And one by resistance, what we call conductance, right? We call it conductance. Okay, conductance is inverse of resistance, and the impedance in the units of ohm. Okay, it's in the units of ohm, but admittance in the unit of inverse or mole or Siemens. Okay, and it is in the form of in the function of G omega. Okay. Anyway. For example, the motor will have both resistance and reactance. Okay. So this part we call resistance. This part we call reactance. Okay, this is reactance. Okay. Okay, let's see some example, right? If we have the capacitance with this value C1 value, okay, C1 value, C1 is 0.01 microfarad, and this resistance is 1 mega ohm, very big resistance, right? Yeah. And in this system, they use 60 Hertz is 2 pi, F is 377, 2 pi 60 is 377. Okay. This is omega. Okay. Here. So the impedance of this part, so C1 will have the impedance of J 1 divided by J omega C, right? We just use this value, right? 1 divided by J omega C to calculate. So these two devices parallel together, we just use the parallel circuit calculation. So we have the impedance with this value, right? So impedance will have both uh, real and imaginary part, right? And we can write down in two forms, polar form or complex form, right? You can convert between this form, right? Your calculator can do that, right? Can convert, right? Polar and complex form, okay? Yeah. Okay. This is the impedance of capacitor here. Okay. And then if the frequency increase to very high value, what happened, right? We just recalculate. This is nothing, okay? It's frequency value, okay? It's changed from very big value to the lower value. You can see that for inductance, the reactance will be J omega L. Capacitance, the reactance will be 1 divided by J omega C. So in this case, omega is 2 pi F. With the circuit with higher frequency, if the frequency increase, the impedance of capacitor decrease. Okay, if the frequency increase, the impedance of inductance decrease, right? If F increase, 2 pi FL. So if F increase, XL increase, right? But in this case, 2 pi FC. If F increase, XC will decrease, right? Okay, XC is decreased in this case. Okay. And in this case, it is the impedance of the inductor, right? If you have inductor and the internal resistance is here, right? We just calculate the inductor with the inductance of 0.098 Henry, right? And the reactance XL will be J2 pi FL, right? Which is 0.098. Okay. Yeah. Just can calculate. Okay, I think nothing so special here, right? Then I would like to make some idea on the how to calculate the complex power. Okay. So in AC phasor system, right? We have voltage and current in phasor form. The power is the voltage in multiply with current, and we put conjugate to current. Okay. So we call this power as the complex power. Complex power is VI conjugate. Okay. S is VI conjugate. Why we put conjugate here? Because when our solution will be complex value, it will be P plus JQ. Okay. The solution will be in the form of P plus JQ. P is the real part of the power, and Q is the imaginary part of the power. Oh, we have never thought that the power also have imaginary part. Why imaginary part? What is that power? This power we call reactive power. Okay. This power we call reactive power. Reactive power. And this power we call real power. Real power. Okay. And usually we use real power, right, in terms of kilowatt. And the reactive power have the unit in kilowatt, right, or watt, or watt. Okay. We know watt, right? We know how many watt of it, but we don't consider watt, uh, real life, right? But in the factory, they need to consider both kilowatt and kilowatt. Okay. So it means that Q is not the power that directly used by the equipment, but is required by the equipment. The Q will flow in and out, flow in and out, and the net value will be zero. Okay, it's an imaginary power. It's there, but it's not used directly. It will flow in and out, okay, from the equipment, and it can be both negative and positive. Okay, both negative and so in this case, if the current lack voltage, okay, let's see like this. If we have voltage here and the current lack voltage by theta I, okay, V is magnitude and I is theta I. When we consider complex power, is V multiply with I. What we get? We will get V I theta I with negative theta I. For example, negative, right? I put negative here for more clearer. Nice. I is negative. When we draw out into two form P plus JQ, what happened? I think I would say in. May I take an example in number? For example, 220, and here is 10 minus 30, right? It means the current lack voltage, and then we will get 220, 2200 minus 30, right? And what is, if you transform into P and Q, what is this? Cos this is 1905, right? 0.25, and this is 1100, right? This is P and this is Q. P and Q, right? Q is negative value. If we multiply V and I, we will get the complex number, right? Real power and reactive power. And if I lack voltage, the current lack voltage by theta, right? The reactive power will be negative. If we calculate without conjugate, right? Here without conjugate. Okay, here without conjugate. Then what does it mean? You can calculate with this system, but you need to remember that the negative value of reactive power is consumed by the equipment. If you have one equipment and the power Q Negative means it's consumed by the equipment. So it's more convenient to use the conjugate form. S is VI conjugate. If we use conjugate, what does it mean? It will be 220, 0 multiplied with 10 minus 30 with conjugate, right? When you put conjugate, you change the sign of the angle, right? Okay, then we got 220, 0 and 30, and then it's 1905.23 plus J11. This is P and this is Q. Okay, it means that this equipment draw reactive both real power and reactive power. It's draw the power. So positive is to notify that P and Q flow in the same direction. Okay, so that's why we use VI conjugate in the calculation. With only V multiplied with I is not popular, not widely used. Okay, it's more widely used in this form, right? VI conjugate. Okay, when we calculate AC power, we use VI conjugate. Okay, so here we use VI conjugate. Okay. And then we will get the power in complex form, right? And we have real power and reactive power. Okay. Okay, then we have one factor called power factor. Power factor is the factor between real power. So power factor is P real power divided by absolute complex power. Okay, with absolute complex power, we call this power factor. Okay. So we have P and Q, and we can calculate the magnitude of complex power. So what is absolute S? It will be square root P square plus Q square, right? So P is real axis, Q in imaginary axis, right? And we can have S in this. Okay. And what is power factor exactly? Well, power factor will be cosine of this angle. P by S, right? Cosine of this angle. P by S, right? P by S. Okay. Okay, let's see one example. I think this may be good for you. Three-phase circuit, right? Maybe next time, right? Maybe this example is okay for today. Okay, let's see this example. We will calculate this circuit in Phasor form, right? We have voltage with this value, right? And the resistance is 4 ohm. L is 8 millihenry. So we transform to XL, which is J omega. JXL is J omega FL, right? And what is the omega? Omega is 377, right? 377. Okay. and the voltage is 14.14. 14.14. What is the RMS value of this voltage? V would be 14.14 divided by square root 2, which is 10, right? And no phase shift. So this is the voltage in phasor form, right? Okay. And the resistance also 4 ohm. And what is the inductance in terms of reactance of phasor form? It would be J377 and then 8 millihenry, right? Minus 3, right? Yeah. And what is this value? That is 3, J3, right? Yes, approximately 3.016, right? So we have this in impedance form. This part will be 4 plus J3, right? Ohm. And we supply voltage here. Can we calculate the current, right? So the current is V divided by impedance, right? We can calculate just similar to Ohm laws. So it's then 10 divided by 4 plus J3, okay? So you can calculate this value, okay? So I don't know, oh, here is sine. Change to cosine form, right? And the voltage is not zero angle, but it is minus 90, right? Minus 90 degree. Sorry. The voltage is minus 90 degree. Minus 90 degree or pi by 2 degree minus here, right? This is a voltage. And this is the impedance. We can calculate the current. So I think you can solve this, okay? And it's become 2 with the angle of minus 2.215. I think they write down this degree in radian unit, okay? You can write in both radian and degree, right? Okay. What are 90 degree mean pi divided by 2 radian, right? And 180 degree mean pi radian, right? You can transform, right? You can transform. It's okay? Okay. This is just write down in terms of radian. It's nothing. Okay. Don't worry about the unit of it. So we can calculate current here, right? Okay. Then we can also calculate P. VI conjugate. We can calculate S by VI conjugate. Then we will get P plus JQ. Okay. Or in this case, more short term to calculate P. P will be real part of this value. So P can be VI cos theta, right? Between I cos theta. Yeah. But anyway, you can just calculate this directly to avoid confuse, okay? And this is the power in form, right? In the form of sinusoid. Okay, I think I will leave this example to make up the mind again, and then I will go to three-phase power, how to calculate three-phase circuit, okay? And then I will give you some okay. So we'll see again on Monday, right? Okay. And I think some homework, you can just start do by yourself, okay? And this is also, you can do it, just make it as a practice, okay? Anyway, you need to do it anyway, okay? Not today, it will be next week. If you do it today, you can do it. Just do it, okay? Okay, I think next time we talk about three-phase AC circuit. Okay, any question?